Today I'm going to talk about the Muon G-2 experiment at Fermilab in the context of other experiments at the lab and other Muon experiments at the lab. The Muon G-2 experiment measures the magnetic dipole moment of the muon, which is the torque experienced by the muon in external magnetic field. Any particle with a spin has an intrinsic magnetic dipole moment, and the experiment directly measures the anomalous part of the magnetic dipole moment. That's done inside the ring, and the anomalous part is the difference between the momentum precession at the black arrows and the red arrows, which is a symbol for the spin precession. So by running the experiment inside the ring, we address directly the anomalous part of the question. The Muon G-2 experiment at Fermilab is not the first experiment of its kind. It's indeed a seventh generation or seventh iteration of these experiments. And the previous one ran at Brookhaven National Lab and measured the anomalous part of magnetic moment down to half of ppm. It's an interesting experiment because the measured number disagrees with the standard model prediction. Here's a summary of what the standard model thinks the anomalous part should be. These are the black points and error bars. And the light blue band on the right side is what the previous experiment measured. And there's the ongoing more than 3 sigma tension between the standard model prediction and the measurement of the experiment. And the goal for the new experiment in Fermilab is to improve the error going down from 540 ppb to 140. If the center value of the measurement doesn't change, it would be the darker blue band here, and it would increase the discrepancy by above 7 sigma. Let me look into how the standard model prediction is made. The anomalous part of dipole moment is dominated by electrodynamics by far. It's more than 99.99% of the contribution. On the other hand, that's the contribution that can be calculated from first principles, and it has been done. All diagrams up to 5 loop have been calculated, and the uncertainty is tiny. It's 10 to minus 5 contribution to the uncertainty of the standard model prediction. Also, the electron V contribution is very small, whether we know his mass or not. It's tiny contribution with a tiny uncertainty. On the other hand, it's the hadronic contributions that dominate the uncertainties. Usually we talk about them as hadronic vacuum polarization. Those are these diagrams, and hadronic light by light. The difference is historically, the hadronic vacuum polarization is something we can measure at colliders. It comes from E plus, E minus experiments like Babar and Bell that rely on the initial state radiation to scan all the energies of the process, or dedicated scanning machines like Novosibirsk experiments. Historically, the light by light contributions come more from lattice. But lately these differences vanish, because not only there are ongoing efforts to improve the numbers, there are new ideas too. There is a Muoni experiment proposed at CERN, and Graziano Venanzoni pushes it ahead. It's an idea to measure the space-like region of the hadron photon vacuum polarization. That's the black curve here on the left side of the plot. And if you compare it to the right side, it's smooth. Unlike the timeline region where there are thresholds and resonances, there are no such things in that space-like region. And the idea is to scatter 150 GeV muons from electrons, and to keep doing it for about 2 years to measure this part accurately enough. Also, the latest calculation is becoming competitive into the hadronic vacuum polarization diagrams. Here's one of the latest results from 2 months ago, where the error bars shrank down to about 1%. And it's interesting because it does not exactly agree with what we And it also is interesting because regardless where this point is, you either get tension with the standard model prediction or a tension with the experimental measured value. But it's a new thing, it's been discussed, and many 3 or 4 other groups are trying to get down to that accuracy too. We think that the discrepancy might hint there's a beyond standard model of physics. The problem with that is we have many candidates and no clear leader. Traditionally, we split the candidates between light new physics, like dark photons, which is simple, very specific model, or dark Z. Also epsilon-like particles. This wouldn't be the QCD epsilons, it would be more like epsilon-like dark matter candidates. And we have many, many SUSY scenarios. Lately, it's been the 2 Higgs double model that seems to be getting traction. There's no clear candidate because everything kind of works, but nothing really works. Let me give you an example for the dark photon. Everything seemed nice and optimistic until NA48 to reanalysis of pi-0 decay showed up at 2015. That's the red tiers here that pretty much closed the last remaining window for the G-2 to live. And also, there's a new Berkeley measurement of running alpha. It's so accurate that it puts tension on of the electron G-2 value. The problem with that is that the muon and electron G-2 numbers prefer opposite direction with respect to standard model. So if you think about Z-like candidate, you would need a vector for one, and you would need a pseudo vector for the other, which is not trivial to get done simultaneously, or doesn't feel very natural. And G-2 is an example of standard model process which we can predict very well and also measure very accurately. But that's not the only way we can search for beyond standard model of physics. The other option is to find a process which is very unlikely to exist in nature. And such a candidate would be a charged lepton flavor violation. We don't know about any absolute symmetry that would prevent that process to exist. Also, we know that flavor violation in leptons was observed in neutrinos. They do oscillate in matter. And the standard model contribution to any branching ratios is typically suppressed by 50 orders of magnitude. And that's what the mu2e experiment and FermiLab is being built for. In the presence of the field of nucleus. And the goal is to improve the previous experimental syndrome by 4 orders of magnitude. The novel idea is a proton beam that comes from backside into a target and creates a cloud of low energy pions that decay into low energy muons. Then there's a section that does momentum selection before it breaks into aluminum layers. That's the nucleus to offer the muon to convert into electrons. When they do, the signal is a monoenergetic line in theory around 105 MeV. In practice, this one is smeared and blurred by energy resolution from 102 to 105, and that's where the problem with backgrounds comes, because the beam-related backgrounds and cosmic ray backgrounds, even muon decay in orbit, can look pretty similar or can reach up to that region in energy. Here's what the decayed muons or electrons see, converted electrons see. It's a Trager planes. It's almost massless Trager planes to measure the momentum of the electrons that accurately. The civil construction of the experiment has been completed. The experiment construction is in progress, and the installation and commissioning is planned to start in 2021, and physics data taking will start in 2023. The experiment shares beamline with muon G-2 and uses 8 GeV protons, unlike G-2 that uses 3 GeV muons. So this will start of mu2e will end G-2. Let me come back to the muon G-2 experiment. Conceptually, it's very simple and straightforward experiment. It measures the ratio of two frequencies. One is the precession frequency of a muon in the field, and the other one is LAMO frequency of free proton. And it's accurate and precise measurement because both these frequencies are counted from the same clock. And the only problem is we cannot measure them at the same time. We either have muons in the ring or the instrumentation to measure field. There's one external number needed, one extra external number needed, which comes from hyperfine splitting in muonium, and it's known better than the needs of the experiment. Still, there is a new experiment museum proposed to improve the number any further. For simplicity, I rearrange that same, that the animal's number is constants we know very well, and only the ratio between the precession of a muon, spin precession of a muon, and magnetic field. The design is straightforward. There are only 4 ingredients in the mix. The details are hard. So we need a source of polarized muons, and its parity violation in pion decay where the polarized muons are born. We need precession proportional only to the anomalous part of magnetic moment, and RIN is a natural solution to that question because it measures directly the differences between momentum and spin. The problem with the RIN is that the muons are constrained in the radial direction by Betatron, but are free to move in vertical direction. And that's where a weak focusing electric field comes in. Then a careful choice of momentum is needed to get rid of the beta cross E term. And finally, we need to move the information on muon spin onto something we can see and detect, which is parity violating decay, parity violation again. And this time it is in positron, in the muon decay into positron. And then it uses only Lorentz boost to map the spin direction onto energy. And the difficult details are the source of polarized muons. It's pion, which is easy to get on paper. It's hard to do in reality. It takes the Fermi-like accelerator complex to get it done. And the path to muons with polarized, well-polarized muons starts in the booster where we have 8 GeV protons. We take them into the recycler ring. We do not accelerate, we only use the recycler ring to rebunch and create very, very narrow bunches in time. Then we take them and hit them into target, which is in piece of inconel to turn 8 GeV protons into 3 GeV muons. Unfortunately, also protons and pions. That's why we use debunchering, the form of debunchering for antiprotons, which is called delivery ring now. And that's where, by time of flight, differences, gaps between protons, pions, and muons are created, and the protons and pions are removed. And then the muons are sent to the muon campus into the ring. Here's only explanation that the ring really helps, the cyclotron motion really helps to address the anomalous part. The terms in the spin precession and the part. However, to contain the beam in the ring, we use electric field, and that's where a new term shows up, beta cross E, multiplied by another term, and we can choose gamma, we can choose the momentum of muons smartly to cancel the term. It's not the only way to get rid of the term. The other one would be to cancel E, and that's the design differences between the muon experiment at Fermilab and J-Park. I'll talk about the differences in a little bit in 2 slides. Finally, we let the muon decay into electron and two neutrinos, and it's the electron that carries information on muon spin because of the parity violation in that decay. The positron prefers spin direction and electron would prefer the opposite direction. And the last step is Lorentz boost that turns the direction into energy. Let me touch on why the electric field is a problem. We can perfectly cancel the contribution for one momentum. However, the momentum distribution is broader. We have high energy momentum, we have low energy momentum. And it's problematic because both the beta cross E terms and these term changes flips signs above and below that. So there is no cancellation, and this is a correction on the size of about half ppm, or the quarter of the discrepancy between the experiment and theory. And there was main motivation for a similar experiment being built at J-Park, not to use any electric field at all. And the design to do that is a magnetic bottler. So it's small vessel, which is magnetic bottler only, and the muons slowly fall down. And as they fall down, they decay, and the decay positrons are measured. Because of the size, it also uses only, it has to use lower energy muons, and that comes with a tall inner spin polarization. Because of the high gamma, the pions decay easily into one direction. It's harder to create polarized muons at such a low energy. And the goal of the experiment is 400 ppd uncertainty, which is comparable to the previous experiment, compared to the 4 times improvement for the Fermilab beyond G-2. Now let me explain briefly how the muons and decay into positrons and how the positrons are detected. So when a muon in the purple decays into a positron, the positron doesn't have sufficient momentum to stay on the orbit. It curves inward, where it in this plot, which is Monte Carlo simulation, the light colors show how many positrons with that energy we have. And as a function of the time, the energy moves from high energy to lower energy. Then by applying energy threshold, we turn this into a plot we can fit into a histogram of below. We can fit. The problem is details. If the energy cut to select effectively spin is unstable as a function of time, it creates fake phase pull, or beam dynamics can change the ridges or the direction of these ridges between the peaks. And the solution, the improvement on top of the previous experiment, was a new calorimeter design. Improvement was in hit time resolution to go down to 100 picosecond. The requirement on deposited energy is weaker. It's only a cut energy cut, but still the goal is to do better than 5% at 2 GeV. And the energy scale stability needs to be in 10 to minus 3 range over the course of 700 microseconds, where the muon rate, the decay rate, varies by 4 orders of magnitude. And also, pile-up is systematic, and to address it, we want to separate events that arrive within 5 nanoseconds and 100%, and at least 66% below 5 nanoseconds. Here's just a little bit of eye candy how the thing is done. You see a render of the calorimeter and the laser calibrated system that makes sure that we know the gain of the calorimeter. The light enters the calorimeter in the same direction as particles. We have lead fluoride crystals, which is only Cherenkov radiator. There's no scintillation, and we use silicon photomultipliers to read out the light. Here's a picture of what it looks in reality, what it looks inside. Practically, the crystals are wrapped into black Tedlar, but for the purpose of illustration, the unwrapped thing is here. And the improvement over previous experiment is silicon photomultipliers as opposed to PMTs. The advantage is these are compact, they work in magnetic field and they do not disturb the magnetic field. That's the camera that reads that the light produced by positrons hitting the light crystals shown on the right. Also, as an improvement over previous experiment, we ran the experiment in the ring from the beginning to the end, and all the processing is done in software later. That required the design of new digitizers. And it's 800 megasample digitizer made by Cornell. Here's just a real recording of that, of two positrons hitting the kilometer in 4.5 nanoseconds apart. Here what it looks in reality when we take the 2D plot, apply the energy threshold, we get a video histogram on the right side, and we fit it with a sine modulated by exponential. The problem is there are many frequencies in the residua. It's the coherent beam motion. It's also the lost muons that do not decay in storage muon, storage volume, and seem to disappear. And it's injection, beam injection. That's where straw trackers come. It's also an improvement on the previous experiment. At 3 points around the ring, we have 8 modules that measure what the muons do inside the ring in a non-intrusive way. They measure the muon profile, they measure the pileup, because we can compare what the trackers and calorimeters see. They detect lost muons escaping the storage region, and they can measure vertical pitch or the tilt of the precession plane, which can be turned into EDM, electric dipole moment as a muon measurement. Here's just eye candy, a snapshot what the trackers, how the trackers see the beam, how they see the energy of positrons to cross-calibrate with calorimeters, and what they think the radial profile of the beam is. We vary the condition because of all the systematics. We vary the run conditions. In run 1, first year running in 2018, we broke the data set into 4 distinct subsets with different systematics. Here's the reason why I did that. The E-field contribution, the field varies from the plates on the side of the storage region to the center, and if the profile of the beam, the number of muons at given momentum changes, it varies the systematics. We do not need big changes. These 4 curves show how large changes we need, and that's the redundancy and extra confidence that our number is done right, because these contributions, these corrections vary from dataset to dataset.
Jarek, you have 5 minutes left for your talk, just to remind you. You have 5 minutes left.
Thank you very much. Here's the example of run 1 spin precession analysis. We had 6 independent analyses, 6 independent groups, using 2 different reconstruction methods from the very beginning to the very end. We had 3 different ideas how to correct, undo, pile up, and 4 different fitting methods. And on the right side, you see the differences between the different analyses. This is a PPM, arbitrary scale, double blinded, and all analyses are within the allowed differences. So the unblinding was encouraging. The total statistical error of run 1 will be 450 ppb, slightly better than the previous experiment, and the method paper is underway. Let me briefly touch on the magnetic part. How do we measure the magnetic field? We use a lot more precision frequency of a free proton. We want to measure where the muons are and when the muons are there. But as a first step, we try to make the field as uniform as possible. There are many shims to be adjusted to get the field that accurate on the ppm level. We use a trolley. Trolley is a device that runs around the ring and measures the field at the same region where the muons are stored. The only problem is the trolley cannot run there when the muons are there. And that's why we have a set of fixed NMR probes above and below the storage region. That's how we propagate the trolley measurements between the trolley runs, how we interpolate the changes when the trolley cannot be there, field changes when the trolley cannot be there. And finally, we compare the probes inside to absolute standard. This is a joint effort at Argonne, joined by Japanese colleagues. So both G-2 experiments will use the same magnet and cross-calibrate the field with respect to each other. Also, the field analysis is ongoing very well. We had 2 independent teams doing 2 different analyses, and they are pretty much on track to meet design goals. Yes, systematic, stable, and goal of the experiment. The experiment finished 3rd year of data taking. We have roughly 7 times more data on tape than the previous experiment. After applying physics quality data cuts, it might be 5 times more. The run-1 analysis, which is 450 ppb, is almost complete, and the systematics appear to be under control. The data from the other 2 years have been processed at the moment, and the run-1 publication is definitely coming this year. So in my conclusions, the Muon G-2 experiment is on track to collect 25 times Brookhaven and improve by factor 4 the result from the previous experiment. The first publication is coming really soon, and it will be slightly better than the previous Brookhaven result. Also, the Mu2E experiment, which is another way to search for beyond standard model of physics, is in construction and will start data taking in 2023. Thank you.
Thank you very much, Jarek, for this very nice overview on muon physics. We have several questions already in the FNQ section, and I encourage you to ask more. I read the first question from Juan Carlos to you. He's asking which nucleus is going to be used in the Mu2E experiment.
It's aluminum. It's a thin sheet of aluminum.
Okay, then we have another question by Alexei Petrov. He's asking, do you expect to put constraints on muon's electric dipole moment as well?
Yes. There is a UK group dedicated to that effort. The result will come a little bit later than the first result of Muon G-2.
There's another question by Yongdu. He's writing, I heard a broken sentence at that time, but it seems you had a comment on the tension between the latest lattice result for leading order hadron vacuum polarization and the R ratio on page 6. Could you please comment again? Given the tension between them, which number shall we trust without bias and why?
There's a group, all these people work together closely, and there is white paper to be published soon that will give recommended number. So that's the number we should trust, that's the number we should use. And as the experiment improves the uncertainty, also all these groups improve their uncertainty, and they meet often to reach a consensus, to give us their recommendations, and they do, and they will keep doing that.
Thank you. We have another question by Lingfeng Li, asking, do you have any extra comments about the electron G-2 in the overall picture?
It's exciting to see how ACME and other experiments, and see how the measurements of running alpha translate on the Muon G-2 and electron G-2. But I do not have any insight. It's another piece of the puzzle where everything seems to somehow work, but nothing really fits. It's not a hint. It's all these problems, discrepancies can be addressed independently, but any solution doesn't seem to help anything else.